The last application of diffraction interferometry are holograms. Now, the book sketches this out briefly, that I'll also repeat. There's no math here whatsoever, that there is no calculations that we can do here, but it's kind of an interesting application to understand. So if we want to make a hologram, the idea is that we make a hologram from an object in front of us. So it's a way of taking a picture. And so a laser comes in, notice again this is a laser, and there's a beam splitter. So we now have taken that initial beam and we've sent it in two ways. One is going to be our reference beam, the other hits our object and bounces off. So we are basically scanning a laser over our object, then the scattered light from our object, the reflected light, comes up and it is going to interfere with the reflected beam in the film. So the film is not just recording a picture of what it sees of the object, it is recording how the scattered light interferes with the reference beam. So that's the idea of recording the hologram. So the record itself is this film which has the interference pattern in it that's been made this way. So to play the hologram back, to see the picture, you shine the laser beam along the reference beam direction, right? So the reference beam had a specific direction, and that's important. The laser beam is shined along that direction. It lights up the hologram, so this is like a piece of plastic, the film now, and then you look at the film and it looks like there's a three-dimensional object behind it. So now what's special about this being different from just like looking through stained glass is that as you move where you're looking, you see a different view of your object. Your object looks like it is really back here and three-dimensional. So that is the special aspect of a hologram. Not just that it's shiny, not just that it's pretty colors, but that you can see a three-dimensional view of your object so that as you tilt your film, it looks like this is moving. So, okay, that seems fine. Now, maybe you've been noticing that this involves the word lasers. And I think it's a little unfair. Most of you, I expect, have seen holograms before. Most of you probably could identify some things around you right now that have holograms on them. And to look at those holograms, you probably don't use a laser. So, if you have a Visa credit card, I know American Express doesn't have this, I don't know about MasterCard or Discover. If you have a Visa credit card, pull that out right now and look on the back of it. There's a little shiny sticker that has like a bird on it. I don't know if it's an eagle or what, but there's a bird, shiny sticker. And that is a hologram. That if you look at it at the kind of with the right angle of light coming in, you see this bird, and as you tilt your card back and forth, it's going to look like the bird itself is rotating. It's not a flat image. If you tilt it up and down, you see the color change. But now what you might notice is that you haven't shined a laser on it. So what the book is talking about right now is a different type of hologram. And in particular, so again, right now you look on your Visa card, you see that bird. If I showed you what this film looks like, this is what it looks like. It's not pretty. It's not reflective. There's no rainbows going on. You don't just look at this and see the three-dimensional image. You must illuminate this with a laser to actually see what's going on. So, what's the difference? This is again a very specific type of hologram, but there's more than one. We can understand the physics behind this type of hologram through interference, through what we've been talking about. However, the little holographic stickers that you would find on your credit card, that you might find on certain documents to prove their authenticity, things like that, those are a different thing. Those are called white light holograms, and the idea being they can just be lit by ambient light. They're still transmission holograms. You're still passing light through it, right? This was being passed through it. And the reason it can work as a sticker is that you put it, basically there's a plastic layer and then there's a foil behind it. So light is shining in through it and then bouncing back off, which is how you can see it. But so the fact that it's lit with white light is how you can kind of also see the fact that the color changes on it as you tilt it one way or another. So understanding the details of how white light holograms work is a different picture. But I do want to point out that when the book talks about holograms, this probably isn't the type of hologram that you're used to seeing. So sorry that the book was trying to trick you, but recognize that even the white light holograms are still about interference. So this is still about having some sort of interference that's recorded, but the white light holograms work better for our everyday life. So kind of a neat application. Some physicists who study optics really like this. And in fact, there are some physicists who do labs where with their students where they make holograms. And in the research lab here at Agnes Scott, I've found a film that looks just like this, right? So I find a piece of plastic that looks like this, and my thought is, oh, this must be a hologram. Now the problem is I have no idea what's recorded here, because this is literally what I see. And in order to play the hologram, I need to know the direction to shine my laser and what color laser to use. So holograms are kind of those weird things that physicists get really excited about it, and lots of people love shiny rainbow stickers. I know I do. But the physics hologram actually is made in this really complicated way and is not the everyday hologram we see on stickers.